Yep, that's correct. Yep. The name Trunks is actually such a weird name. I don't know. It just Sam is not my mom. Come on, Brad. You gotta know the family tree. Susanna correct. Parents. Sam. Yeah.
You go, guy.
That. Yeah, but we don't have that. No one's called by their real names in the family. Yeah, no. Such a ugly name. Almost. We'll take it though. Mr. Myers, do you mind just going back to J for 1 second?
Yep.
Just can I see what you got for it? 9x squared plus 12x. Okay, thank you.
All right. Ladies and gentlemen, please make sure this is automatic. The ability to expand polynomials and in the very next unit, reverse that expansion is to higher level math what the times tables are to your math up till now. Do you understand? If you know your times tables, like know them, not have to do if I say what's 8 times 7, and you take 1 second to go 56, that's knowing how to multiply. That's not knowing your times tables. Do you understand the difference? If you know your times tables, 2 to 12, automatically, math is, up till now, is made infinitely easier. The next level is to know how to do this automatically. You'll notice that for most of this, I showed no work. Right? The ability to reverse this is also equally important to higher level mathematics. Okay? Are we good with it? It's just the exponent laws, right? All right. Page 314. 314, idiot. 114. 314. The book doesn't even go to page 314. Thank goodness. I'd be teaching forever. Now, I already heard my good friend Miss Walton discussing one of the 9th grade teachers, and he'd already gone over this, and that's cool. I just want to make sure, again, it's important in that these definitions are part of your answers later on. Okay? And we'll talk about what that means in a minute. But right now, we're just going to talk about these. If I were to pretend we were all in kindergarten, and I were to be at the front of the room, and I were to say, class, today is the 8th day of April. let's count how many days there are so far in April. And you would all go, okay, Mr. Myers. Some of you wouldn't. Some of you would still be scared even this late in the year. You would still say, okay, teacher. Some of you wouldn't even do that. Some of you would hide. Some of you would be eating your hair. Some of you would be in the corner crying. This is what happens in kindergarten. I know this. My wife teaches it. But those of you that could would say, okay, Mr. Myers. And I would go, and you would all go, and we would start, and we would go 1, 2, and we would be forgetting a very important number because nobody starts counting with 0, even though it's really the first number. Because all of us naturally start counting at the number 1, that is what we define as the natural numbers.
I've always had a question, and I wanted to ask somebody, is 0 an odd or an even number?
Neither.
Because some schools sometimes.
It is neither. You cannot divide 0, right? I mean, you technically can. You still have 0. So I suppose by that definition, you would say 0 is an even number because it is divisible. But it is also an odd number because you can't divide it by 2 because you still have 0. You don't get a new answer. So I like that question, though. Natural numbers are our counting numbers. So the number that we start with was what again? 1. And what's the next number? 2. And the next number? And when will we stop? Never. We can count forever. Will we ever get there? No. So these numbers go up to infinity. Eventually we stop naming numbers. But the next number after the last number we've named is just that number plus 1. So it goes forever and we will never get there. Is everybody cool? Easy peasy, right? Excellent. Next one. Whole numbers. Now, up until either Mr. L's class last year or this class right now, whole numbers for you people have to deal with fractions, right? If I wrote this, don't write this down, 4 2/3, and I asked what's the whole number there, you'd say 4, right? That's not what it means in number theory. In number theory, whole numbers are the natural numbers. So every natural number plus 0. It is exactly one number bigger than natural numbers. So they will go 0, and then we'll change color back to blue because that's what we used. Hey, Miss Jansen, what can I do for you?
Just grabbing an envelope
Okay.
full of money. Thank you.
Yeah. Subtle. You know.
Toonies for days.
Hey. So notice, and it still goes up till infinity. Now, what I'm about to say isn't actually true, but it helps my students. Whole numbers are ever so slightly a bigger set of numbers than natural numbers. Even though natural numbers go to infinity, these have that one more little spot. Everybody cool? Now, being the... Yes, Ken. Yes, I know, go. Being the intelligent young people that you are, we have another category. Well, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to infinity, does not include a whole whack of numbers, right? What numbers are missing? Negatives. So integers are our whole numbers plus our negatives. So they go negative infinity, which exists, up to -1, 0. Oh, sorry. Then we start with our whole numbers, and then we are back into our natural numbers up to positive infinity. Is everybody cool to there? Everybody good? Okay, now, please notice there is even another bunch of numbers that we haven't talked about. They are, of course, the fractions and the decimals. We're going to talk about them in a minute. This is where math starts getting bothersome for you back in the day. Grade 3, you all could count. What grade are you in? You mean grade 3? How many grades have you been in school? 3, 1, 2, 3. Right? Right? Okay. You also all know 3 because that was how a great many of your parents disciplined you. Go clean your room. Okay. Go clean your room. No. 1. And then you went and cleaned your room. And then your mom said, go clean your room. And you went, no. And your mom went, 1. You were like, no. And your mom went, 1, 2. And you're like, damn it. And you left and cleaned your room. Then, here's a little hint for all of you. At that point, your mom was scared. Because your mom didn't want to have to get to 3. Because at 3, in my day, 3 was followed immediately by a backhand. You guys don't have that, some of you. So your mom, you were like, no, 1, no, 2, no, and your mom went, what did your mom do? 2.5. And you're like, what the hell is this half? Now, if your mom is good at math, how long can she count before she gets to 3? Forever. Why? Because you can keep cutting it in half. 2 3/4, 2 7/8, 2 15/16, 2 31/32, right? And she'll never ever get there. That was where math, for most of you people, went from you guys who ended up here in pre-dip to the kids that are like, whoa, I can go from 1 to 2, and there's infinity in the middle there. Now, of course, there's a third level of kids that never got past 1 and 2. But what? What? When DeVries closes my door?
Yeah.
I like it too. It was Radnai?
No.
No. Okay. So, rational numbers are all the other numbers between these, but there's some rules. Rational number must, I should use a different color that I haven't used yet. Rational numbers must be in this form. X over Y. X and Y must be integers, and Y cannot equal 0. You can't have a denominator of 0, and X and Y must be integers. So some number between negative infinity and positive infinity with no decimals in either of those. So what does that cover? That covers every single fraction is automatically a rational number. And every single fraction that's a proper rational number is also a decimal. But that decimal has rules too. It must repeat or terminate. And terminate means end. Everybody cool? So, is this a rational number?
Yeah.
3 is an integer, 4 is an integer. The denominator isn't 0, so it's rational. Is this a rational number? Yes. Why? It's a decimal that ends. Is that a rational number? Yes. Why?
Because it's repeating.
Because the 2 repeats. Is this a rational number? Yes. Why? Because it ends. Is this a rational number? Okay, good. Is this a rational number? This is the problem one. There's no line over it, so it continues, but it's repeating a 2 so far. But do we know if the millionth decimal point isn't going to be a 7? No, we don't. So this, we can say, appears rational, but we do not know for sure. Is everybody cool? All right. Now, being the intelligent young people that you are, without writing this down, tell me if this is a rational number. It is. Why? Because this is 1/2 times 8/3, which is 8 over 6, which is 1 2/6, which is 1 1/3, which is 4/3, which is rational. Is everybody cool?
Yeah.
I know. Yes.
Wait, what do you guys
Is that a rational number?
Yeah, no. No, I wasn't knowing you. I was doing it.
It's cool. Is that a rational number? Of course it is. Why? Because that is 4 2/10, which is 42 tenths over 3 1/10, which is 31 tenths, which is 42 tenths times 10 31sts, which is 420 over 310, which is 42 over 31, and it's rational. Is everyone cool? Excellent. Being the intelligent young people that you are, if there are rational numbers, there must therefore be irrational numbers. And those irrational numbers are numbers that don't meet any of these standards. What's the most famous one? Pi. Somebody always says right here, but Mr. Myers, pi equals the circumference divided by the diameter. That's a fraction, isn't it? Right? But it's not. Because when we do circumference divided by the diameter, we round that off. Okay? In a perfect circle, the circumference and the diameter are never rational numbers. They can't both be rational, or this wouldn't be rational. Everybody cool? All right. There's a bunch of other famous ones that are symbols like this. There's another one that looks like an E. You can see it on your calculator if you look at it. It's like pi. It equals like 2.78 blah, 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 blah. We use it in financial math and in things like that. But for our purposes, the irrational numbers that we are worried about are the square roots that don't work. Okay? For example, square root of 1 is 1. Square root of 2 is, if you do that on a calculator, you get 1.414, and your whole calculator screen fills up, right? If your calculator screen fills up without showing any type of pattern, you get to assume that it is an irrational number. Everybody cool? Now, the only time we get into trouble with this rule is things like this. The square root of 1.44. A lot of people will look at that and say, that can't have a square root. It's a fraction. Blah. But it's, of course, 1.2 when you use your calculator. So this is still a rational number. But if you tried to do 1.45, your screen would fill up. Is everybody good? Easy peasy lemon squeezy. Now, there's one other thing I am going to warn you about, but I'm not going to teach you about it. What is the title of this page? Real number system. These are the numbers that really exist. There's another whole set of numbers called the imaginary number system. So after you're done learning all the math you need with the real number system, they'll teach you about the imaginary ones. You don't have to worry about it until very high level physics and calculus. Okay, you heard about it last year, I'm sure. Did you do any work with them? Crazy line weaver, really?
No.
It's things like this, the square root of a negative number. Right? It doesn't really exist because you can't have a square root of a negative number. It's things like that. Is everybody cool? All right. Turn the page over. Let's see how much we know about number theory. I want a fraction from that. What is it? 12 over 100. Would Mrs. Bag Crumble let you hand that in as an answer? No, she would not. I know this because my kids just went through elementary school. That would be marked wrong, even though it's right. 3 over 25. Right? Easy peasy lemon squeezy, no problem. Now, listen please. I trust that all of you already know this trick. But if you do know this trick, I'm going to ask you to be quiet for a moment and let the few people that don't know it figure it out. What is that as a fraction? If you know the answer, you can say the answer, but don't say how you got it. What is that as a fraction? 1 over? It is 1 over 9. Can you explain why? Okay, Sale, can you explain why? No. You know it's 1 over 9 because you had a math teacher at some point tell you, if there's a repeating number, it's over 9, right? Okay, that's wonderful. Not particularly useful. That's kind of like saying if you put gas in your car will go. Doesn't really explain why the car goes. So, we're going to talk about this for a moment. What is this? If I were to write it all the way out, what would it be? 0.111111. For how long? Forever and ever and ever and ever and ever. Agreed? Right? Okay. What is just that as a fraction? 1/10. Agreed? Is the light blue number bigger or smaller than the gold number? Bigger, ever so slightly, yes? This is 10 cents. This is 11.1 cents, right? It's ever so slightly bigger, yes? So if I want this as a fraction, it has to be x over y, doesn't it? And both x and y have to be integers, don't they? Well, obviously it has to be 1 on the top, just like 1/10. What is the next integer in fractions that is bigger than 10? No, in fractions. Would you rather have a 10th, an 11th, or a 9th of my pizza? A 9th, because that's the biggest piece. That is why it's 9. Does everybody understand? Sale.
But then, okay, 1/9 is equal to 0.1 or 3.
Yes.
Then why is 9/9 equal to just 1?
Because you have the same thing on the top and the same thing on the bottom.
But then wouldn't be 0.9 repeating?
Okay. 0.9 repeating, true, goes on for how long? To infinity, right? So I have 0.99999999999999999 forever, yes? So at some point I'm going to be out at the quintillionth decimal place, right? Which makes me 1 quintillionth less than 1, doesn't it? What is that in reality? 1, right? That's why.
So it's like a limit.
Yes, it is exactly a limit, which is where this will come to in year 2 for you guys when you start that stuff. You will start doing limits. Kind of like halfway between you and me. Will I ever get to you? If I cut the distance between you and me in half, will I ever get to you? No. Right? In reality, do we bump into each other? Like if we're 20 feet apart, right? If I go 10, 5, 2.5, 1.7, or 1.25, eventually we'll smack into each other, right? In reality. Will I mathematically? No, I will never get to you. Do you all understand? Okay? Everyone cool? All right. So now, what is our best guess for that as a fraction? 2/9. Beauty. Easy peasy lemon squeezy. Now, what's that? Okay, so one of our guesses is 54 over 99. So I'm going to get out my calculator, my trusty calculator here. And I'm going to go 54 divided by 99. 0.545454. Is that this? No, because what's this? 0.54444444. All right, so why did we want to, one sec, let me ask my question, then you go. Why did we want to put it over 99? What about this made us want to use a 9 in the denominator?
Because we know that repeating numbers.
We know that it's repeating, so there must be a 9 involved, yes? Okay, Anu, what were you going to say? 1/2 plus, so you have 1/2, the 0.5 plus 4 over 90. Why is it 90? You do know why it's 90. You just need to think about it for a sec. Why did I need to add this 0? Why isn't it 4 over 9?
Because there's a number in front of it.
Because I'm out a bracket. Not a bracket. I'm out a place value. Okay? That's one of the tricks to use. Now let's see if he's right. What's 1/2? 0.5. Duh. What's 4 divided by 90? 4. There it is. That's one of the tricks. There's another trick. That's 1. This is what I was taught when I was your guys' age. Another way. I got to be over 9 because there's something repeating, right? But this doesn't repeat. So I'm going to use 0 because it does nothing. Everybody cool? And then it's not 54. 54 is what would totally repeat, but what's missing? That 5. So here I was taught to go 54 minus the stuff that doesn't repeat to get 49 over 90, which is the same thing. That was the trick I was taught. This is what Anu just figured out, I assume, or were you taught that as a trick? Be honest. Good. Everybody cool? Everyone cool? It's pretty easy, right?
Which one would you prefer?
It doesn't matter.
Okay.
Doesn't matter.
Okay.
In reality, do you think I really care?
No.
What would I really say if I were saying, hey, give me this as a fraction, and you told me it was about 55%? Don't you think I'd be happy with that? Yeah. Because what would be in the real world? You owe me 55% of the bill before I finish the job. Well, I'm only going to pay you 54.5444. Like, okay, right? All right. Okay, A, B, C, D, E, F, G. Put them in the right category. Remember, if something is natural, it's odd, or if something is an integer, it's automatically whole and it's automatically other way around. It was right the first time. If something's natural, it's automatically whole and an integer. Okay? If something fits in the smallest group, it fits in all the groups.
So do you want us writing all the groups?
No.
Whatever.
The biggest group into which it fits.
Okay.
Or the smallest group into which it fits.
Wait. The smallest group. So
Yes.
9 is a natural number then.
9 is natural. If it's natural, it's automatically rational, it's automatically whole, it's automatically an integer.
Yeah, because you put it because it's the smallest group.
And after we finish this page, I'll tell you why this is important.
So you'd only be a decimal, but it ends.
You only write the group that it fits into. Of course.
Okay. You know what? We're gonna go with that.
You know what's right, dude. Does 14 have a cube root? 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is
27.
27.
8. Let's go.
Was there anything between 2 and 3? Which is where that would have to be, right? Because it's between 8 and 27, right?
Yes.
So what is that?
Some ugliness.
An ugly root, which makes it irrational.
Love that. Okay, what about if it's a nice root?
Then it's rational. Well, it might be more. You put it in the smallest group into which it fits.
Okay, well, what if the answer would give you a natural number?
Then that's what it is.
Which one is where the decimals come in?
Rationals.
This one is this one. Decided
Like that.
If you're not sure, leave it blank. It's just notes. As soon as we're done this page, like I said, I'll tell you why it's important.
No. Well, that's what you get.
Okay, what's B? Since everyone's talking, everyone's done. What's B?
Natural.
Why is it natural?
Because 5 is natural.
Because that equals 5. And if 5 is natural, it's automatically whole, it's automatically an integer, and it's automatically rational. What about that? Rational. Why? It ends. As a fraction, that's 5 and 319,754 millionths. Right? What about that one? Natural. Why? Because it's 16. What about that one? Natural. How old are you? I'm 9. When you were 9. I know it's blue. Nice. Some guy on the PlayStation Network just sent my kid a message like, hey, I'm playing this game that you play. You want to play like head to head? And my son's like, I don't know if I'm going to answer. And while he was waiting to answer, the guy says, "How old are you?"
Oh,
And my son says, "People don't usually ask that, so I'm probably not going to answer because it could be somebody creepy." And I was like, "Dude, that's funny because when you're like 5, how many of you guys have like 5-year-olds in your lives right now? Any of you? Like a little brother or a cousin or something? What's the first thing they ask when they run into another kid? How old are you? And they say, well, I'm 5, and I'm 5 too. I'm 5. When's your birthday? Well, my birthday's in June. Mine's in January. I'm older than you. I'm in charge. Right? But that stops somewhere along the line. You got to stop asking each other how old you are. I don't really know when it happens. But apparently for my son, it happens around 14. When did it? My son is 14.
what?
Yes. He's 14. When did you remember 14? He's a natural number. Okay. What's F? What's F? Imaginary.
That's a trick question.
It was a trick question. What is G? It appears rational. Why? But do we know for sure? No. Excellent. Now listen, please. Here is why this is important. And this is for your people's high school lives, what I'm about to tell you, this is the only reason it's important. Sometimes when you're counting stuff or when you're graphing stuff, you can't have decimals. For example, if I was counting people in this room if I was graphing it against time, could I have decimals? I could. Half of you could leave the room. Your legs could walk out, leaving your body and your arms here doing work. No. Every time somebody left the room, what would happen to the amount of people in the room? It would go down by one whole number. Everybody understand? That's where this is important. When you're doing physics, for example, you're going to use a lot of decimals. But if you're doing biology, you can't remove half a cell. You understand what I'm saying? That's where this comes into play. Now the bell is about to ring. Jesse? Yeah. Of course there is. But what I'm saying, for you guys, you'll be faced with things like X, all your X values have to be whole numbers. That's what I mean. And in that case, when you do the work, when you come out with a decimal, you have to round it off. Kind of like when we were doing cans of paint or degrees. We weren't using decimals of degrees. We were using whole numbers. It's so easy. It will take you 5 seconds and the answers are there. Page 116 is your homework.